So thank you, everyone. This is a pretty good showing, especially given some challenging times in different work situations and homework balance situations. So thank you for taking time out of your day to join us here today. So this is another seminar. It's part of the NASA Survey's Analogs Focus Group, which we've just started up in the past year or so. And our plan right now, we're having quarterly seminar series in an attempt to bring the analogs community together, the science community and the exploration community, to share the different types of research that's being done and to help foster collaborations and to basically optimize the science and exploration that we can do here on our home planet, and that can inform what we do on planets and planetary bodies throughout the solar system. So thank you for joining. This talk is recorded. Many thanks to NASA SURVEY, the Solar System Exploration Research Virtual Institute. They're based at NASA Ames Research Center in California, which is where I also am based and I work there. So they're recording this. It will be edited to make it flow, and then that will be posted online. So I will send out the link when this talk is posted, because we actually have a fair number of people who watch the videos and watch the seminars after the fact. So there's a lot of people online now, which is great, and thanks also to the folks who watch this later as your schedule permits. So I don't take up too much time. I want to introduce our speaker today, R Skok, who is at the SETI Institute right now. He's been doing a lot of fascinating research in a variety of terrestrial analog environments for many years now, and I'm excited to hear about his talk today, Martian Hydrothermal Analogs in Iceland, Exploring the Ancient, Altering, and Modern Analog Springs for Biosignatures. So we will let JR take over, and then we can also have time for questions afterwards, time permitting. So JR, I think you're good to go.
Thank you, Jen, for organizing. I know it's, I agreed to do this a few months ago, back when the world was completely different. So it's been interesting seeing how things have evolved to get to this point, but glad that these online sessions and forums for sharing science still exist, and we can go ahead. So honored to be here. Thank you for SURVEY for this opportunity. And I'm going to share some work I've done in Iceland to understand the features, the analogs there, how we can study them to get a better sense of Mars. And I think there's some motion. If people want to mute, that might help background noise. And how we can kind of go to a new place and systematically find analogs, compare them to features we want to study, and how we can get a better sense of how to do science on other planets. I was fortunate enough to win one of the first P-STAR grants when that program just started. So this work comes out of a NASA P-STAR funded project to understand how to research hot spring environments on Mars to look for habitability for future exploration of hot spring environments on Mars. So let's see here. Trying to advance. Okay. So like many people who work in Mars science, a lot of the efforts these days are focused on finding habitability. That's what motivates so much of the work. A lot of the top priorities of the main landed missions with Perseverance, the Mars 2020 rover, going out trying to find habitability. And so you know, for years before we settled on the Jezero site, there was a big debate in the community of what is the best places to look for habitable environments, what are the best places to look for habitability and biosignatures on Mars. And so, you know, this is a kind of debate that, you know, we had in the landing site workshop communities for that mission for years. And when we try to find habitability, we're looking for four main things for finding life on Mars. We need a place, an environment that life can develop, a place that has the water, energy, protection from the environment, the chemicals that life as we know it needs. We need some mechanism to concentrate those biosignatures. If it's just like one cell in a large collection of rocks, it might be hard to find one signature. But we need a way, some mechanism, geological mechanism, to concentrate biosignatures. Then we need a method of preservation. Most likely, a lot of the life that could have happened on Mars would have happened a long time ago when Mars environment was a lot more conductive to habitability. And we need some mechanism to preserve those signatures until today. And finally, we need some sort of landform detectability so we know where to look. You know, Mars has a lot of area, and we need some geology that we can see from the surface, some mineralogy, morphology, something that we can see from the orbit, from remote sensing, to say this is a place to look. And so three different kind of regimes of geological environments have usually come to the top of landing site discussions. One of the most common ones is sedimentary lakes and river deltas. That's one of the reasons why we went to Gustav Crater with the Spirit rover. It's led us to Gale with Curiosity, and is now driving the push towards Jezero for the Perseverance rover. This is a place where you would have evidence of water, and really what sets sedimentary lakes and deltas apart is this method of preservation, where you have clay deposits that are really good at preserving biosignatures on Earth, and we're hoping, searching through these kind of deep clay beds that we see on Jezero, could be a place for preserving life. Another constant finalist on landing sites is deep crustal hydrothermal environments, places where you've exposed deep crust that would have lots of heat, lots of water for long periods of time, creating a very nice place for life to develop, and then hopefully exposed for exploration. That's always had an issue on whether or not they've had the right minerals for preserving biosignatures or how to concentrate them. A lot of work has been gone during the Landsat workshop to show that places like Northeast Syrtis, which we believe is a deep crustal hydrothermal site, is a place to search for habitability and possibly biosignatures. And hopefully if the Perseverance rover has a long mission, we might be able to get to some deep crustal exposures in the midway kind of extended mission plan. So during this discussion, I pitched Nili Patera. It's a caldera site, which is a volcanic hydrothermal site. So this is a more concentrated and usually smaller hydrothermal place where you have a focused, volcanically heated, focused hot spring environment that is a great place for life to develop, a great place for the mechanism of water flow to concentrate biosignatures in certain places. It's a place that has some great preservation capabilities, as well as a place that we can see from orbit. So I'll talk a bit more about those places, but these are the three different places that we often look for habitability. And because my focus has been on this volcanic hydrothermal, that drove my selection of field sites that I'll be talking about in this talk. So diving more into why we care about hydrothermal sites, just briefly, is that here's a list of how different materials can preserve fossil records. And silica is what we get from hot spring environments. And it's the mineral that kind of precipitates out of the fluids. And it's just one of the most stable ways of preserving biosignatures for hundreds of millions of years. We see this all over Earth, and we're hoping that this mineral on Mars could have long-term preservational abilities. So kind of motivating our selection of field sites are discovery of two different silica hot spring sites on Mars. One is the home plate. It was one of the finalists for the Perseverance rover, and was explored by the Spirit rover a number of years ago. And finding high silica deposits as well as digitate structures led scientists to think that this was at least a fumarole and possibly even a hot spring silica center site that could support life once upon a time and provided the mechanisms to preserve it. Another one was based on work I've done in the Nili Patera caldera of Sirius Major to find other silica mineral deposits in a kind of volcanic field. And since this is what motivated the Iceland work, I'm going to dive a little bit more into that environment and what we want to know about it to explore that possibly someday in a future habitable mission to Mars. So Nili Patera is located inside the Sirius Major volcano. It's one of the darkest, most dust-free places on Mars. It's the first place on Mars ever mapped in a telescope in the earliest sketches in the 1600s, and just a great volcanic structure. Inside it is a caldera, a collapse feature with very complex geology. And we're going to focus in on this Nili Tholus. It's a volcanic cone, and these little white spots that are around it you can see in the upper corner here, where we have the arrows. So here is a kind of perspective view focusing on the cone and some of these white mounds. When we look at the spectra here, we see this 2.21 micron absorption feature that indicates hydrated or moderately hydrated silica centers, possibly. We definitely know there's silica there, and cinder is a different term that I'll get to in a moment. But we know that these are point spots of silica. The kind of volcanic terrain around them does not have this signature. So these white deposits, point spots, are the silica. And the best way that fits that with both the composition as well as the morphology is that these are once hot spring deposits that were precipitating silica as the water came out and would evaporate or lose the water in the atmosphere or surface of Mars. So we've mapped an entire field of these. So this isn't just like one spot, but we see this entire field of this mineral. And so here we see a perspective view showing this fan, this white tone fan in front of us. Looks possibly a spring may have come out of this cone and then deposited silica as it flowed down, as well as this mound structure that we'll come back to this a bit more as we talk about some of the field site comparisons, but this mound structure is also this silica mineral that we've mapped to it. So now the kind of geological environment we're looking at. So this is a kind of cross section of a caldera. And we are looking at the very top parts, the cinder deposits and hot springs that would be manifested at the very surface of a caldera. But the surface deposits is just kind of the very skin of the entire system. There's a connected hydrothermal that goes deep on Mars and then is represented by these samples, these materials at the top. And so on Mars, if Mars ever did have life, we believe that it could still have life today deep under the surface where you have enough water and heat still on Mars today to have life. And finding this way to bridge the surface and the interior is a real challenge. We can't dig that deep. We believe now that there is a cryosphere that kind of really seals deep Mars from shallow Mars. But once upon a time, if there was a deep biosphere on Mars, hot springs may have been a kind of connection between what is deep and what's on surface. And that was a concept that we wanted to explore a bit. How would we study that? How would we see if maybe the deposits on the surface could contain what might be a deep signature of biosignatures? So that's kind of the motivation of how do we use surface deposits to kind of look at deep Mars as part of this as well. So that set up the questions we want to know about Martian hot springs. How, if we actually landed at Neoptera or at Gusev, what biosignatures can we search for? What kind of minerals would kind of indicate that this is a place for biosignatures? How do we actually want to explore this? Can we do it with a rover? Do we need to have a whole laboratory, or does it require for humans? And then what instruments do we need to kind of look at this field at the bottom here, this big rubble pile of rocks, and say, oh, this is the bit of rock we want to test for either sample return or analysis or imaging. How do we pick which rocks? So these are the questions that motivate the analog work that we did in Iceland. So then we started searching for great analog hot springs on Earth. And these is a map from Campbell in 2015 that looked at all the center sites on Earth. And I've been lucky to take some of the work I've done and work in El Tatio in Chile, in New Zealand, as well as in Yellowstone. But of all these places, one of the ones that has the most diversity, as well as some of the best Mars-like basic geology, was in Iceland. And so that is what made us focus this study on the sites in Iceland. It's the diversity of sites and the kind of basic Mars, basaltic volcanism. So volcanism, the diversity of features, as well as Iceland, despite kind of having a bit of a remoteness to it, it's really easy to do work in. It's a fairly easy flight from major airports in the US and Europe. It's a fairly small country, so it's a couple hours in the car to just about any place in the country. And it's a very science-friendly nation. Like permits and sampling was much easier than you get in, like, say, national parks in the US, which often have a lot more red tape that you have to go through for sampling. So the diversity of features of planetary analogs in Iceland are just stunning. You have glaciers, hydrothermal alteration, volcanoes, a whole host of sites for almost any kind of old Mars and volcanic planetary analog you can imagine. It's always amazing whenever I fly through the airport in Reykjavik. Very likely to find some friend I didn't know who was going to Iceland, just either there for their own scientific expedition or just there for traveling. It's a magnet for planetary scientists of all types to kind of see these planetary features in action. So we started to look for the right field sites, the specific sites that would give us insight into the hot springs on Mars. So Iceland is a little unique because it's a mix of two different types of volcanism. It's a hotspot volcanism that comes from a deep mantle melting, sitting right on top of a shallow mantle melting mid-ocean ridge. So you have two different kind of regimes of volcanism that combines to create this volcanic wonderland that is Iceland. So right now, this is a map of current volcanic activity. The main center of Iceland is where the current activity and therefore geothermal energy is mostly directed. But throughout the kind of east and west of Iceland, you have older samples that were also interested for us to understand the evolution of how hot springs and these kind of systems could be. So here's a map from the geothermal industry in Iceland. Now, most of the electricity in Iceland comes from geothermal activity. The volcanic resources there, the geothermal resources there is incredibly well used to power much of the country. And so they've done a lot of study focusing on the geothermal resources that are around. So the kind of red dots here are the high temperature places that when water comes out of the surface, it's boiling. And then all the black dots are low temperature areas that are also of some interest because they could have been sinter sites in the past or possibly still depositing sinters in some form today. So my first job when I went to Iceland was to talk to some scientists based there and wanted to know where the best sinter sites were. I got some maps, but a lot of work was focused on where geothermal energy was, and that helps indicate where we might want to look for sinters, but not always exactly where sinters are. So my first 2 weeks of field work was going to as many of these geothermal regions as possible to try and see whether or not the sinters were what I wanted. So I went there, I would do initial field works, try to understand what, do a drone mapping to get a sense of what the distribution was. I went in Reykjavik and bought this thermal pools in Iceland. So like the bonus of it is by finding the best hot springs on on Iceland, you get to find where these good hot spring analogs are. So, the hardships of science is exploring some of the hot springs and hot pools of Iceland in the process. So now, as I start to get more specific, I want to just distinguish some terms and how I use them. So a hot spring is a very general term for wherever this hot water comes out of the surface. So usually about 70 degrees, above 70 degrees is usually where we start saying hot springs. Oftentimes they're boiling, but not always. And now I'll often use the word sinter, and sinter I'll typically use to mean a kind of physical mineral that precipitates from hot spring waters. This is usually kind of something that you see in the surface. So if you see this mineral coming out of the water, it will be called sinter as a general physical identification. It's usually silica is the mineral. Sometimes it could be calcium carbonates, it's travertine, or other minerals, sometimes even oxides are kind of heavily represented in these minerals. But sinter is usually kind of the physical term when I talk about a mineral. And then silica, when I use it, I usually mean kind of a more mineralogical term. And this I use mostly when I talk about the silicas on Mars, because we have compositional information there for remote sensing, especially in Neoptera, but we don't have kind of the physical confirmation. We have sinters. So if I say silica sinters, then it's both the kind of physical texture as well as the composition. But if I use one or the other, it usually means either physical or kind of specifically compositional for what it means. So it's just kind of a little definition of how these words are a little different as I use them. So looking back on the timeline of Mars, this is a pretty detailed timeline of different trends on Mars history, going from 0 years ago today to 4 billion years ago in ancient Mars. And the big takeaway here is that a lot was going on in early Mars. That's when we had all the volcanic activity, so we had a lot of water activity. So hydrothermal Mars would have been very active for 3.5 to 4 billion years ago in this Noachian era. But every single rock we ever pick up on Mars exists today in the Amazonian. So when we want to understand a rock today as it might record ancient habitability in Mars, we need to also consider kind of the trek that it takes to get to modern instruments today. So when we looking for hot spring sites, we want to find a place that looks like what Mars is today. So this kind of Neoptera, Amazonian Mars, like something that looks like what if we're on Mars today we'll find, so we know how to explore this. But we also want to know a bit about how these rocks, these hot spring deposits, the fossilization, all that would have happened when it initially occurred. So we want to find a place that looks like what Mars was when it was more active 4 billion years ago. And then in between we have a long stretch of time where we expect a variety of changes on the surface of Mars. We expect it to dry out, get wet, go through alterations, a long period of time. So when we try to find analogs in Iceland, we want to find field sites that could kind of represent these three eras of Mars. Someplace that, modern Mars, something that we can practice exploring what we'd find today. We want to find what the environments would have been like when they formed to understand how life would have actually, formed, evolved, fossilized. We know where to look, and then have a sense of how it would alter. So after searching dozens and dozens of field sites for the right centers, for the right kind of environmental conditions, we settled on these three places scattered around kind of central and western Iceland. And so the rest of the talk will be kind of diving into each one of these to talk about how we pick the site, how it is to work on, and the kind of point in time in Mars history that we're hoping to learn and ask questions about it. So one of the things after 2 summers in Iceland that I could never quite do is get a good sense of the Icelandic pronunciation. So I'm going to probably butcher these names, and I completely apologize for that. But we're going to start in the center Iceland in the highlands. And so this HV is actually, I think, pronounced like as a K sound. So I think this is usually pronounced as a Kálfur. And then we'll go down to the southwest in Gunavir, and then over to the western Iceland in Lysol. And so these 3 places we'll kind of explore in more detail as we march through time on Mars using these Icelandic analogs to help guide us. So yeah, so we'll go from Milwaukee and ancient active Mars in Kálfur to kind of a more altering, drier, but still warm volcanic Hesperian Mars in Gunavir, to what these hot springs would look like today, possibly on Amazonian Mars in Lysol. So a bit about the field site in Kálfur. It's located in the highlands of Iceland. And this is one of the more kind of limiting field sites for our study. It's because it's in the highlands, it gets very cold, very inaccessible as a dirt road to get to. Luckily, it's only 4 hours from Reykjavik, and it goes by fast. You have to go through the town of Geyser with the famous namesake of Geyser. So it's a beautiful drive to get there. But you can only go for about 2 to 2.5 months in the middle of summer when the snows melt and the roads open up. So that one you kind of have to plan your field season around the most. It's a tourist destination. It's really one of the only kind of oases on this long road through central West Iceland. It has basic accommodations, usually tent camping for most tourists, a few cabins. Luckily, though, it has an on-site weather station that researchers there can rent out, and that really helped our ability to live comfortably while doing this intricate sampling and observations for days. And so the science we've done here is kind of looking for, so on the way there, you have to drive to the highlands of Iceland. And this is like one of the more planetary analog landscapes that I've seen. It's incredibly barren, empty terrain, very inhospitable until in the last few decades, they've started building these dirt roads. And when they're not flooded and they're not completely mudded out, you can actually drive through and start accessing this very kind of remote Icelandic terrain. So after like 2 hours on this road, after another 2 hours on the paved roads, you finally get to the nice little hot spring oasis that creates enough water, enough warmth that you have plants growing in the middle of that kind of dry, desert landscape. And it forms plants, it forms kind of nice water. You even have sheep grazing nearby usually. And it's a nice little environmental oasis surrounded by this barren highlands. So here we have just a variety of really active hydrothermal features, from hot springs to some places with more fumarole activity, active center formations. You have different biological environments. You even have relic centers kind of all around here, kind of intermixed with the active sites as the hydrothermal conduits have kind of altered over the last few centuries. A lot of current microbial growth and fossilization, and it's in a national park, so you do need to get tourist permits to sample and to kind of go off the trail here. So we did all that and were able to explore. So in this area, we really want to know, like, where in these systems does life form? Where in the environment of the hot spring does life like to live? How is it actually preserved? Where in the system is it actually preserved the best, so we know we can find what markers? And then how do we find the minerals and textures that can really mark, say, hey, this is a place to look for biosignatures. So this is an overhead view of the system. We have springs up here to the in this area, and then they'd flow downhill towards kind of the runoff zones off to the screen there. So this here is kind of the blue pools in the area. It's just a beautiful color water full of this silica kind of dissolved inside the fluids. And now, so this one is not the best sinter kind of depositing springs of it, but places like here where we have this sinter mound building up with this steam vent and a number of other kind of pools that use this kind of silica-filled saturated waters to precipitate out the minerals we're looking for, and hopefully will preserve the life that we might want to find someday on Mars. So here is a sketch of kind of the cross-section of an idealized hot spring vent where water will come through the throat in the vent. You immediately have like most of your silica deposition because you have the silica saturated waters, which hits the atmosphere, cools down, and starts to really deposit materials and builds up structures. Usually this water is often boiling when it comes out, and that can create kind of turbulence that leads to kind of finger-like geyserites that kind of indicates that you're near a vent. And then the water begins to flow and continues to precipitate out sinters as all these different features, from terraces and terracets to a number of different defined features. Not every hot spring will have each one of these, but this is kind of very, kind of a combination of many different hot springs that will, create a variety of these depending on their particular qualities and how long they've been forming and flow rates and all that particulars. So in this kind of structure, I think this was mostly built from looking largely at New Zealand examples, but a lot of the basic terms are universal to hot springs wherever we look for them. So zooming in on this one kind of picture of the hot spring origin sites in Color, we see active pools here, where we have the sinters being formed out as concentric kind of terraces around the pool. We see older vents that have now shut off that are nearby. So it's not just a site isn't just active and then goes and has a route. Becomes dry, but you have this, like, within a single site, you have this like temporal diversity where you can have younger sites overprinting onto older sites. And as we try to unlock history of hot springs on Mars in these places, understanding this kind of superposition, how these different sites form, might help us understand the history of water flow, how long it might have lasted, where's the best place to find buried deposits if that's what we're looking for, and a variety of other kind of understanding the micro actions in these environments that might lead to discovering where biosignatures are preserved. So looking at the vents, we see both active vents and these relic vents. These are places where we have most of the silica deposition, but it's also a place where in these systems we often don't have the best preservation for life. Because the nature of when this water comes out of the vent, it's usually boiling. Any cells that might have been in the water column in deep earth would have probably been ripped apart by just the boiling action. So you get a lot more deposition than you have fossilization in some of these terraces around the vent. And again, that really depends on water temperature and activity and water amount. But as a rule, while this is not, we're still doing ongoing work to do like SEM work to actually look at the habitability here. But for the most part, this is not the highest concentration of biosignatures. But we'll get back to that later on whether or not how that might change for Mars. So if we go farther down to mid-apron pools, distal aprons, this is a place where on Earth, in many hot springs on Earth, as well as in Iceland, we see most of the life forming. It turns out that because life on Earth is very abundant and most life on Earth is photosynthetic, what we find is that the majority of life we find, these streamer fabrics from these bacteria and other life forms, they like the kind of protection, the warm energy of the water, but they get a lot of the energy from photosynthetic operations. And then, so that allows them to grow very robust. And so even though there's far less precipitation of silica in these environments, they often preserve a lot of these textures more when they do, because you have a lot of bioload. And so any precipitation happens, you capture a lot of the life in these kind of mid-apron terracets environments. So here we see more of that, just showing all these colors are formed from different strains of life that then are available for kind of mid-apron fossilization in these systems. So on Earth, in a environment that has lots of options for photosynthetic life, this mid-apron pool is kind of the hotspot that we found for finding fossils for life living in the hot springs. In other places where there's a lot more robust life, such as plants, we find a lot of centrification of grasses and marshes if we go farther out into the system. So both of those, we have to question that if we take this to Mars, what is the likelihood of marshes being there once upon a time? So that's not a typical expectation for finding the types of life on Mars we want. So, but still on Earth, the terracets is usually a good indication of finding where you have a stable environment with enough energy for life to happen. One idea is that possibly on Mars, especially if we want to connect to this life that might be on deep Mars, looking for life near the throat, looking in the geyserites, places where you have a lot of precipitation of silica, you might possibly be able to fossilize any kind of biosignatures that might be in this water column here, as long as the kind of boiling process doesn't kind of rip them apart in the process. So that is a way that Mars might be different. But if we're on a site like this, it's important to know how to find, identify where the vent was in 4 billion-year-old systems, and where kind of more mid-apron environments would be like. So yeah, so here looks at this kind of like the geyserite textures you find where you have a bit bubbling and water motion that leads to these kind of digitate features around the vent. And so textures like this help you tell where vents would have formed. So next we're going to move to a more altering Mars in Grunewald. This is very close to the international airport, just about a half-hour drive south of there. This is a place that has lots of tourists. It's fairly easy, so you get a lot of bus groups who are driving from the airport to the big, the blue hot springs that you always see in the advertisements, and then they usually stop here. A bus will come, stare at this constant smoker that's our steamer that's always blasting away, and will come and visit. They'll watch what you're doing as you're doing your science, and then they'll go away, and you'll have a period of quiet as you continue your work. So this was a place that used to be hot springs, centered building hot springs. As late as 100 years ago, there was some written reports that this was still active pools. Then in the 70s or so, they built this power plant, geothermal power plant nearby, and a lot of the groundwater table dropped. So you had this drying out of the hydrothermal system here. So it went from being kind of center producing to more fumarolic activity, where you still had the geothermal heat, but you didn't really have the water. And so this is where we wanted to understand how does, we expect on Mars that any kind of wet environment would go through long periods of dry that would still, keep on the initial thermal properties, volcanic properties, but have various regimes of how wet it was. So we wanted to come here and understand what happens when this area dries out, but it still has geothermal activity. And so that's what we wanted to study here. And so how do the centers alter with time? How does that affect the biosignatures? How does that affect what minerals and markers we're going to look for? And how can we explore this kind of topography to look for the minerals we're looking for? So here's an oblique view of this mountain that we did as our second field site. All this kind of yellow white material is the centers that have then been altered by sulfur deposits from the fumaroles. And it's on top of this kind of very altered kind of volcanic rock soil, oxide heavy soils underneath it. So we're going to look over at this area from the walkway there. And we see here the remnants of an old hot spring pool. And so this is a place where we can say, oh, here is kind of the center of a vent. Looking from above it, you can see the kind of circular outcrops around it, and the depression was once probably a vent. Kind of looks like what we saw in Colorado, but dry and having undergone this kind of alteration and fumarole activity. So in this area, when we look at the mineral changes, we find that basically this whole area, if you like put your hand close to it, it's all hot. In the right lighting, and if it rains recently, you see steam coming up almost anywhere. And with this, you find that it brings a lot more sulfur minerals are activated and brought up in the steam and start to encrust so many of the rocks. So when we see this, like with spectra, we brought a spectrometer to this area and start mapping it, we see vast amounts of sulfur kind of encrusting the centers and other rocks here. And that is an indication where we had this kind of fumarolic alteration kind of working away at the centers, despite the fact that a lot of the kind of general depositional layers are still present. They're now overprinted by this sulfur-rich minerals and kind of alteration. We were able to drill in, this is about a 2-inch diameter drill hole, and it was just stunning. Like when we talked about the centers being one of the most robust preservation rocks that we know of, when we tried to like actually drill through some of these altered zones, it basically fell apart and almost felt like a styrofoam texture because of the geothermal fumarole activity just kind of really altered and weakened this rock. And so part of the study that I won't get into today, but we're working on, is understanding how that alteration basically would have destroyed or changed the fossilization and the biosignature preservation ability. So knowing, seeing that sulfur shows that we have this fumarole activity in the history of the field site might indicate places where preservation of the centers is very much weakened and may not be the best place to look for it. So this is where we can use minerals to maybe not show where we should study, but show where we should avoid for the best biosignature preservation sites. So this here is a topographic map made from overlay made from a drone mapping that we're working on. And so it is about the same dimensions wide as this mound that we have in Nilo Patera. It's about 1/2 as high, but it gives us a sense of how we might be able to study that. And so this is some of the studies we've done with cameras of how, like, if we were coming up to this mound, how do we find, how do we reconstruct the mounds and the vents and the springs from views that we might get as we approach it. So this is some of the additional studies that we started to do, and that once we decide what kind of mission this would be, we can have a better sense of what is the exploration process of reconstructing hot spring structures in the kind of topography we might find on Mars. One of the grad student on this, Marisol from ASU, she worked with Jack Farmer to map these environments so that way we could actually do these reconstructions, went out and found out where all the paleo vents were, where all the terra sets were, and allowed us to kind of really build back through time, through alteration, what these environments were. So we know where the terra sets, where the vents were, and can pick out the pieces of the system that might tell us about how life, if we find life on Mars, what are the environments, what are the temperatures, what are the pHs, what are all those pieces are, which change where you are based on where you are in the vent, what they may have liked if we found them. So doing this kind of paleo reconstruction of vents would be important to not only find where we should target for biological searches, signature searches, but what that life might have liked, what it might have been like if we do find it. So our third site is in Leishhall in Western Iceland. It's on a private ranch, and it's about a 2-hour drive through pretty nice roads from Reykjavik. You need to get owner's permission, but they're very friendly, very eager to help out scientists to use their land to understand other planets. Local accommodations are available there, so we were able to actually stay in a very nice guest house with amazing breakfasts and walk over to our field site when we were there. This is mostly a site looking for, so this is actually one of the most beautiful sites. So this is a kind of picture from a volcano nearby, and our field site's actually tucked away in this little valley there. The volcano I'm standing on is on the very western edge of this peninsula, and if you are a literary fan, it is the place where in Jules Verne's Journey to the Center of the Earth, it's where the characters there entered the Earth to start their journey. So that's the volcano we're standing on to look on this beautiful volcanic ridge to ocean view, and so it's a very beautiful place to do field work for a bit. So back to the field site. This is a giant center field in the middle of the horse ranch. It's very difficult to date silica centers. There's not a lot of usually good radioactive elements that we can use for dating. But based on the volcanic history, we expect this to be somewhere between 5,000 and 10,000 years old is when the major volcanic activity in here had the last spurt. And so this would have been sometime after that, although the exact date is of the range of this. And there's many different hot springs within this unit. So there's probably a long range of different centers of vents that would have built up this field. It's surprisingly seen from the surface. The white are cinder deposits that just don't really grow the grass. So it's surprising how well this old deposit was visible to our studies. So the key questions that we want to study here is, this was our best example of what it would be like to actually show up on Terra and Mars today. Old centers, on Mars, they're many magnitudes of years older, but much less active of a surface than we'd have in Iceland. So how do we go to this kind of rubble pile that we find in Iceland and find habitability? How do we find the biosignatures? How do we go about reconstructing that? And so what are the key minerals we're looking for? What are the identifying textures? And how do we reconstruct that were the main questions we wanted to answer here. So this is kind of a zoomed up or kind of a drone photo of this area to kind of show generally what we're trying to work with. This was once, this kind of rubble pile here was once the main center of one of the vents that we want to study. And so because these centers are so hydrated when they're formed, as they get older and dehydrate, they really like to break apart. So this kind of center breccia is seen in almost any relic hot spring site on Earth. And it's a very common kind of textual process. So if we had silica in a center environment, we very much expect this kind of brecciation to occur. So how do we start to reconstruct that? So also, this is a working horse farm, so we had these visitors come by every once in a while. They also helped kind of cause some of the brecciation, we believe, as their footprints were often found breaking up rocks, and they really enjoyed to chew on any cables we had for equipment, which was a fun little challenge to keep the day interesting. So here is our car and our trailer. So it kind of gives you a sense of the scale. It's a fairly large system, and we find probably about at least 6 to maybe a bit more paleo vents that would have been center areas of kind of the hot spring origins that would have formed mostly in this area and then flow down, and a few more in this more north zone. So then this led to kind of the old traditional geological work of just starting to put your nose to the rocks, trying to find out, getting layers like this and trying to hunt for the clues that tell you where in the system you are. So a lot of rocks like this. So when we found kind of competent rocks like this outcrop compared to the breccia, this was kind of an indication that we were getting close to the vent structures. They were the most coherent, the most strong, and kind of preserved bedrock the best. And a lot of it became this kind of massive cinder. So this is all kind of the silica cinders that you really can't see a lot of textures with a hand lens size. It's just kind of this massive kind of hollow, a very kind of vesicle-rich, surprisingly light but very hard silica rock that was found throughout the site. So this is like a lot of what we're walking through to try and figure out where we are in the system. And so when we got to the heart of the centers, heart of the hot springs, we'd find these kind of structures. We find these concentric layers that would kind of point back to where we had flow, where we had the kind of layer after layer of center production. So it was these kind of structures that say, hey, this is pointing back to where we would probably have a vent, a throat structure, trying to find whether or not there's any leftover geyser right nearby, or which of the textures that trace us back that might have been present in the system when there would have been life and precipitation, and hoping that this will tell us, what might be preserved in this part of the proximal to the vent system. This area happened to be flowing into a major marsh back when it was active. So a lot of the area we found was this plant rich. These are all grasses and stems that have been centrified. So, this is like the best possible hope for biosignature finding on Mars if we have macro biosignatures trapped in centers. So this, very good biosignature found in Iceland, most likely on Mars, we won't find anything this obvious of body fossils preserved in the centers. So then we mapped, provided kind of general mapping for most of the hot spring system and very detailed mapping of where the vents and near proximal vent structures were. So again, a lot of this was finding rocks inside the breccia, finding, some places were better preserved than others, where even we can find long stretches of these terracets. So we can kind of say, oh, this is in this mid-apron flow area. Based on the sizes and the kind of distance of the terracets, we can start to estimate possible depositional rates as well as speeds and some of those other key questions kind of written inside the rocks. And a lot of it is finding, chunks like this inside this breccia melange. And so, that's the kind of detective work of how do we build back these systems and how do we want to understand where in the system are, and then we can start picking in each and every one of these different parts of the spring to understand what is the biological potential. Ideally, it looks like if we want to find physical biosignatures in these areas, using the SEM, either in situ or with returns, is probably the main way to go to find physical biosignatures in these particular environments. So yeah, so that was the main goal here, and that work is still ongoing. And as we understand, if this ever gets pushed on to closer to a mission idea to go to hot spring sites, this would be a great place to bring kind of the technology you want to bring, what instruments you actually want to bring. Part of my team is working on building a SEM that we can take to Mars. And so bringing those into the field here to understand how do you pick which 2 millimeter sample from this 100-meter wide field do you want to study, is a good kind of practice for bringing those instruments to Mars to understand how to visually reconstruct these systems where we want to sample, and how do we select based on mineralogy and textures which places have the best potential for biosignature preservation. And so one of the best nights I had at this particular field site is I had my team work out late, and in late September we had a beautiful northern lights kind of keep us company as we continue to kind of capture the last few possible hours of field work with headlamps, doing some GPR analysis underneath the northern lights. So most of the summer, if you work there in Iceland, you don't get any night times, but if you can keep your project going into September, it gets just dark enough to enjoy beautiful sites like this above your field areas. So always a thank you to my team who made this work possible. A whole collection of great scientists who helped us understand the site and are continuing working on this now, and will hopefully push us towards a better understanding that we can take to build the instruments and the techniques and explore future habitable sites on Mars. So with that, I can take questions about the field sites, how to take your work to Iceland, or questions about the work I did.
Fantastic. Thank you, JR. That was a really great talk. We have muted everyone, so if you'd like to ask a question, you'll need to unmute yourself in the Zoom, and then we can do that. So while you figure out where the unmute button is, there's a bunch of them. There's one in the lower left. There's one if you hover over your picture. There's one if you have a participant list and you hover over your name. So try and figure that out. Send me a chat in the Zoom box if you have questions. So while people unmute themselves, I have a couple questions, JR. So I have 2 questions. One, so I've only done fieldwork in Iceland once, and I was perhaps naively surprised at how wet it was, especially around Reykjavik. So I'm wondering if your field sites are wet, like rain, bog, that sort of thing. And since Mars is so dry, how that plays into or doesn't into the preservation potential of what you're seeing in Iceland and how that compares to Mars. And then my second question is, you were mentioning it's the mid-apron pool areas which sort of have the highest potential for the search for life. So I'm wondering if, based on your boots on the ground experience in these analog environments, what are your thoughts on the trafficability of getting to those kinds of areas? Like, can you get a rover up there? Can it traverse that terrain? Are you gonna fall through? Like, what you think about access?
So the first question, yeah, Iceland is incredibly wet just about everywhere. It rains even in the highlands. You have rain and snow melt, so that we could never really get away from water in most of our field sites. We didn't deal too much rain. We had very few days where we completely rained out, but just constant moisture or wetness was a common issue. The biggest problem that happened to us is when we were trying to take advantage of the fact that Mars 2020 was going to be bringing a ground penetrating radar to their study to understand how would GPR be able to show us what's buried on the surface. Maybe, if we could find a buried, mid-apron, mid-aprons, underneath a few centimeters or 10 centimeters of other centers, if we could use GPR in Iceland, that might help us understand what we're looking for in these kind of sites on Mars. But GPR does not work well when it is saturated grounds. So we found that a lot of our GPR was really hard to get good signals on because the grounds on Iceland were just so saturated that, under a few centimeters of centers, we quickly hit like really bright groundwater reflectors that were hard to make signals out after that. And so, that's a particular challenge to the Iceland that we had, that analogs on Mars where you have much drier conditions that you would not expect to get in an instrument. As far as like the preservation issue, that's a tougher one. Like we try to, we mostly focus on the physical biosignatures because that is what centers do best to preserve over 4 billion years. I think the water issue would probably be less of an issue when looking for these physical center biosignatures, although there still probably would be an effect. But, if you're looking at Mars, especially something that's 4 billion years old, it would have been probably very wet early on. So, I think it's a hard thing to directly compare against, and it's definitely just something that you need to definitely put as a caveat whenever you're making that comparison. Okay, so that was the first question on the water. Sorry, could you repeat the second one? Just remind me.
Oh, it was about trafficability and access to the mid-apron pool areas.
So so in the active system, getting around was incredibly hard because everything collapses and you burn your feet and it's really dangerous. But once they kind of cool off, everything becomes hard and solid. And then, especially because when you're at the mid-apron pools, almost by definition, it's more of a flat area. You kind of slow down your flow rate. And so trafficability, I think, becomes a lot easier there. We saw it on the mound where you have, mound pools at the top and then they start flowing off. But I think wherever you have kind of the mid-apron pools, it tends to be a bit flatter and everything tends to be a lot more solid once it's been cool for a long time. So, when we looked at the Leichel field site, unless you're with, like, basically most of the mid-apron areas were much flatter or at least gentle slopes. It's only when you got to the main vent areas that you had enough rocks and boulders where driving over would take challenge depending on, just how big your wheels are. So on Mars, we saw that like the one mound down here that's 20 meters tall. And so I think that, if you had a Curiosity kind of rover system there, it's definitely a way to navigate that. There might be some routes better than others to make sure you don't hit the wrong slope, but I don't see that as a critical dilemma. But, as we figure out which type of system we'd explore, then you could do the better analysis.
Okay, thank you. I see that Scott Hughes is unmuted, so I'm going to guess that Scott might have a question. And then also we have a question in the chat box, so we'll let Scott go first if you have a question, Scott. And if anyone else has questions, feel free to put them in the chat box and I will read them to JR.
Thanks, Jen. A great talk, JR. I really enjoyed your overview of all the different varieties. But what got me thinking from the very beginning was your spectral signature of sinter and other silica deposits. As you know, a lot of these volcanic systems, and especially some of the drier ones, can produce other forms of silica, cryptocrystalline silica specifically, in the form of agate or jasper or other chalcedony, whatever. But is there enough difference in spectral signatures between those minerals and the actual sinter deposits that you could discern that on the surface of Mars?
So it depends a little bit on the form. The biggest thing is, if we have completely dehydrated silica, so like quartz, something like that, we can tell the difference between hydrated silica, which is what we see in Niliptera, and something that's completely dry. So that's something, because we see the hydration bands, even though they're a little bit weak in Niliptera, they're definitely there. So we can tell it's not, pure silica. It's a hydrated silica of some sort. quantifying how hydrated that is much more difficult. So the biggest thing that, like, when we look at Nilipatera, for example, it's kind of this, the fan-shaped deposits, the point deposits, the kind of point source nature of these deposits is what kind of pushes, I think, my understanding towards the hot spring end of the formation mechanism in this particular environment. If you go to Home Plate and Gustav Crater, they see what they propose to be digitate structures, which requires more of a water flow. So in that place where we do have ground data, that one I think looks, that one, whether or not digitates are an actual biosignature is one of the big debates we had during the landing site workshop. Some people believe that digitates have to form from life. Others say that you can form from wind and other water processes, but I haven't yet heard good ways to form those processes without water around. So it's kind of a mix of the physical textures as well as kind of the landscape that makes these particular places seem more like hot springs, sinter, depositional environments. There's a number of other places where we find silica across Mars that we believe is probably more of like a drier, more volcanic formed alteration process that isn't related to hot springs. So we're find a lot of silica, and only these places right now are leading cases for being kind of hot spring point source formations for it.
Got it. One real quick comment about that. We know from Yellowstone work that we have 3 different types of hot springs: the high pH, the low pH, and the neutral pH. Neutral pH is with the where the most of the center is, the dissolved silica. High pH for travertine, and low pH is where you get the mud pots, because that's the alteration. So it seems to me that there should be a control on by groundwater. If you have high groundwater, you're going to get the neutral pH springs. If you have low groundwater far away, you're going to get the alteration into the the clays, and of course sulfurous deposits with sulfuric acid. Yeah, I was just wondering if that is something that's going to be of consideration and really mess up your analysis or not. But that's just something to think about. I was not aware of all the different varieties you find in Iceland. I think it's a good place to discover those sorts of things.
Yeah, so we see all those types in Iceland, of course. We focus a lot on the neutral ones where we have the sinter formation, because they're the best ones for preserving the sinter biosignatures. But I would imagine, and when we look at these places in Yellowstone and Iceland, we're looking at a very fraction of time. In any one place, when you look over the history of time, you'd expect changes in groundwater level to change the actual environment you have. So you'd expect, some periods where in Iceland, where you have more rain, more water flow, you end up with this more sinter-producing environments from the high ground level. And then, we saw in Grunewald, where the groundwater dropped because of a geothermal plant, we moved to a different regime. So I would think that if we go to any one of these sites, we'll probably find imprints of all the different regimes in any one place. So we'd find a lot more evidence of this, sinter, because that's just what forms materials the best. But then, we'd expect that to dry up before, just through the, cyclical nature of Mars, we'd expect it to get drier while volcanoes are still heating to change that regime. So that was why we wanted to focus on that aspect in Iceland, is how do we pull out the different regime periods from a single site? So it's definitely an important question to understand that pathway.
Great, thanks.
Great, okay, we'll have one more question. Don Hood, do you want to ask it yourself, or would you like me to read from the chat?
I can just ask it, it's fine. Hey, JR, so you mentioned briefly bringing a handheld spectrometer to the sites. Did you do any look at the available remote IR, and see how it compares, and if you can see any changes between the sites in the remote data?
Yeah, so we had the cameras on the surface, so we were able to do imaging spectrometry. We did not have a hand point IR, so we brought samples back, and we were able to do that in the lab. So that wasn't able to, so we were able to do like mineral conformations, but not do kind of mapping ground truth with a point IR. One of the challenges here is we did not have great access to remote IR for these sites. either because just having high level, these areas are pretty small, so a lot of the general hyperspectral instruments that are available did not have great coverage for here, just because of the pixel size was an issue for remote data. And a lot of the places like Crovere in the Highlands, it's so wet that the spectra we had was not, you didn't really see good silica signatures just because of how wet and atmospheric absorptions. So it was really hard to do the kind of comparison we'd really want to do with that from remote. And this project did not have the funds to do kind of a plain fly with the instrument we wanted. So unfortunately, we got good spectra from the ground, good point spectra from the lab, but we weren't able to really compare it to remote spectra yet.
Okay, thanks.
Thank you.
Okay, well, we are exactly at the top of the hour, so this is probably a good time to stop. And thank you, JR, for agreeing to proceed and give this talk, despite everything that's going on in the world. We really appreciate it. And thanks everyone for joining in and for folks who watch this afterwards. So I hope you all have a good rest of your day, and we'll see you at the next talk, if not before.
If people have any questions, if you want to do your work in Iceland, I've always loved to share the field notes I have and give recommendation for sites and how to handle permitting. So if people have any more questions, just contact me. You can probably find me on the SETI site, or I'm always an email away if people have questions.
Perfect. Thanks, JR.
Thank you.
And thanks, everybody.